in all of its aspects are incredible. But we know that there's physics and life and questions beyond the standard model. And aside from just the interest of doing something important and fun at the new IFT building, this is what pushes us forward. There are experimental indications, clearly, that we must go beyond the standard model to understand dark matter, the only form of matter really discovered by astrophysicists so far. Neutrino masses, baryon asymmetry, we still do not understand, although maybe that's just a theoretical problem. And of course the cosmic acceleration. And then there are theoretical puzzles that us theorists think we should be able to understand, such as the unification of those three Maxwellian-like forces, which at their heart are all the same and fit together so beautifully together with the matter multiplets. The hierarchy problem, or the electroweak scale compared to the unification or Planck scale. The flavor masses, mixings, generations, total mysteries. Shelley described, but with no real idea, no success. And of course, cosmology, which is now a quantitative science and gives us mysteries that we must explain. To me, among these clues, experimental and theoretical, the ones that have pointed in a fascinating new direction is supersymmetry, and motivated, phenomenologically motivated by these three fundamental problems: observational and theoretical. And supersymmetry, invented for other reasons, first discovered in string theory, beautiful extension of ordinary space-time and its symmetries to allow for quantum dimensions, naturally gave explanations, or gives explanations, potential explanations for these problems. It's a very compelling case, which is, of course, why it is one of the main foci of the experimental program at the LHC. It is beautiful and predictive. Supersymmetric models have dozens and dozens of parameters, but they're all in the symmetry breaking sector. The theory as itself, just take the supersymmetric model, make it supersymmetric, has no new parameters. That's incredibly predictive. Of course, the symmetry is broken, and there we have many ideas, many models, and many parameters. And there's nothing beautiful about our attempts to break the symmetry, which one could say also about the Higgs sector. What we've learned so far from the LHC is is that colored particles are not around the corner. Those are the ones we would have seen immediately. Many models predict, and some of phase space has been ruled out, especially that we would have seen these colored particles. Now let me turn to the other reason why I love supersymmetry, not just phenomenology, and the answer to those three important problems, but as a theorist. Anyone who has studied supersymmetry, and with all the developments of especially the last decade, cannot relinquish this. It's like Einstein said about his theory when confronted by experiments that seemed to contradict it. He can't believe that nature would not have taken advantage of such a beautiful structure. In using supersymmetry, and in recent years, I believe we have found finally a wonderful playing ground for theorists, what might be called the hydrogen atom of quantum field theory. The hydrogen atom, or in general, the 1 over r squared system of two particles, played an incredibly important role in the history of physics. This was an integrable theory with enough symmetry to allow one to write down a simple, complete solution, which was a good approximation to the real world. And it, of course, we are very lucky that such a simple integrable system played such an important role both in gravity and in the motion of the Earth around the Sun, which is the good approximation given by this integrable system, and of course in the case of the hydrogen atom. If Newton didn't have such a simple integrable system to start with, it would have been much harder to develop the laws of classical mechanics. And certainly the Bohr model, which happened to be an exact solution to the hydrogen atom using a semi-classical approximation to a theory which wasn't known, was exact because it was an integrable model. And that enabled Bohr to make the crucial step that led to quantum mechanics, to understand the periodic table, and eventually to, within a few years, within a decade, to the greatest revolution I think that physics has gone, that of quantum mechanics. Also the Dirac equation and its simplicity, which motivated relativistic quantum mechanics and quantum field theory. We were lucky to have the hydrogen atom, an integrable model, which, to a very good approximation, since the fine structure constant is small, approximated the real world. In two-dimensional model field theories, we've had a galore of integrable models, which have played a crucial role in our understanding both of quantum field theory, its renormalization, normalization group, anomalies, and many other features of quantum field theory. But in 4 dimensions, until recently, that's been lacking. However, gauge theories, which play a big role in the standard model, cannot be really tackled. Even QCD, which has sort of no parameters, and for large momenta is a simple theory. For small momenta, strong coupling is intractable except by numerical techniques. On the other hand, we seem to have found in the supersymmetric, maximally supersymmetric cousin of QCD, with maximal maximal supersymmetry, a integrable model similar to the hydrogen atom, perhaps, not as close to nature, of course, and so the n equals 4 supersymmetric gauge theory with an infinite number of colors, and the first step in an approximation to this quantum field theory in 1 over mc is, it is believed with great certitude, integrable. There are an infinite number of conserved quantities which allow one to write down the solution of this theory exactly on a piece of paper. No lattice computations required. And much of this theory has been solved by now. It's very annoying. I see your frustration. It's just too small for a clumsy hand like mine. And much of this large N theory has been solved. The complete spectrum which is an infinite number of states, has been calculated. And maybe Nemo will discuss the completion of that, the final steps of solving that theory in the large N limit. Now, this is an incredibly useful tool, I believe, as it always has been in the history of physics. And we're just beginning to make full use of it. To go back to QCD, which is a cousin with less supersymmetry, one has to break the supersymmetry and put in quarks. That can be done, but you lose many of the nice features of the starting point. But eventually that might be one of the real ways where we will be able to analytically, on pencil and paper and not with computers, calculate properties of QCD. More interesting, it is dual to a string theory. It is believed by now by everyone that it is rigorously mathematically equivalent to string theory in a particular anti-de Sitter negative cosmological constant background. So this is not just a beautiful model anyone has looked at, falls in love with, but useful. And it already has proven to be extremely useful to a diverse set of community of physicists. It's useful for calculating QCD scattering amplitudes. Nima might discuss that. It has been useful for discovering properties, qualitative properties of the quark-gluon liquid that exists when quarks are deconfined at high temperature and and large density, as in RIC, collisions of heavy ions. And it's now becoming a useful tool in many-body theory. We just had a 3-month program, very exciting, at the KITP on so-called ADS-CMT, using the duality between string theory, solving Einstein's equations in some approximation, and the study of quantum critical points, which are believed perhaps to explain high-temperature superconductors. It's not only useful, I believe, but important, because the understanding of that gauge theory side of this profound duality with string theory connects to many of the deepest issues that face us in our attempts to understand quantum gravity, black holes, the Big Bang, emergent space-time, and string theory, and field theory. And the two, we're learning, are the same.